Welcome to the lecture on software pipelining. So, software pipelining is a new type of optimization at the machine code level. So, what exactly is pipelining? Everybody is familiar with the hardware pipelining concept. So, there are different pipeline stages through which for example, an instruction flows fetch, decode and so on and so forth. So, similarly software pipelining implies overlapping execution of instructions from multiple iterations of a loop. So, hardware pipelining is in hardware there are different phases of stages of a pipeline and the same instruction flows through all these stages. But in software pipelining we want to make sure that instructions from different iterations, not necessarily the same iteration, are also permitted to use the functional units of the processor. So, that the stalls are actually minimal, all the pipelines are kept busy and the hardware pipelines are kept busy without any stalls. So, we mix instructions from different iterations of the loop. So, in other words software pipelining is meant for a loop, it is not meant for simple straight line code. So, what is the objective of software pipelining? Basically, to sustain a very high initiation rate. In other words, we want to start execution of as many instructions as possible, in a single cycle if possible. So, initiation of subsequent iterations may be done may start even before the previous iteration is complete. So, if there are not enough instructions in the same iteration which can be started in a particular cycle, then it is possible that instructions from the second or third iteration ahead may be actually started right now. But then on what basis does one do all this? Obviously, dependencies between instructions, that is if an instruction produces a result and it is used 5 cycles later, you really cannot say I will start the instruction which is using it much earlier than 5 cycles later, that is not possible. But definitely when there are no dependencies which hurt, the instructions can be from other iterations can also be started. So, unrolling loop several times and performing global scheduling on the unroll loop is also a possibility for increasing the parallelism, rather harnessing the parallelism available in programs. This exploits greater instruction level parallelism within the unrolled iterations. So, for example, if we unroll the loop once, then 2 iterations of the loop will be executed as straight line code one after another in the body of the loop, and parallelism available in these 2 iterations will be utilized. And if we do it 3 times, then the parallelism in 3 iterations will be used and so on and so forth. But there is not much overlap across iterations of the loop. So, in other words, if we can start the second, third, fourth iteration instructions in the same cycle, this unrolling mechanism will not help. Of course, you may say why not unroll the loop 5 times and then start instructions, but then the body of the loop really becomes very large. There is a code blob attached to loop unrolling. Then there are 2 approaches to software pipelining. One is called iterative modulo scheduling and the other is called slack scheduling. In iterative modulo scheduling, we use a mechanism or a methodology which is very similar to instruction scheduling, that is list scheduling algorithm, and we compute priorities as in the instruction scheduling algorithms, and we use operation scheduling here. Okay. So, in the case of instruction scheduling, we used to utilize cycle by cycle scheduling, but here as a rule we use only operation scheduling. The reason is very simple. The reason is we use the modulo reservation table instead of the global reservation table. What is an MRT, modulo reservation table? So, this is a global resource reservation table with its II columns. In other words, II is the initiation interval which will become that is every II cycles I am going to start a new iteration. Okay. So, that is what initiation interval is. There are II columns and R rows. R is the number of resources in the system. So, we really do not have a table which is as large as the schedule of the entire program. That is what a global reservation table is, but here we have just II columns and R rows. Okay. So, instead of T columns where T is the length of the schedule, and MRT records resource usage of the schedule for the kernel. Okay. So, what is a kernel? That is the set of instructions which are within what is known as a core of a software pipeline. This will become very clear very soon. And the usage of resources for that entire program which is inside the kernel is actually recorded in the modulo reservation table. Why is it called modulo? Well, all the resource usages actually are recorded with time modulo II. So, for example, initially all the entries are 0, but if an instruction uses a resource little r at time step t, then the entry MRT r comma t mod II is set to 1. So, that is how it would be. So, everything is modulo the initiation interval. Slack scheduling is similar, only thing is it uses earliest and latest issue times, that is the deadlines for each instruction, and the difference is slack. We have seen this before in the instruction scheduling algorithms, and it schedules an instruction or rather tries to schedule an instruction within its slack. So, here also we require the modulo reservation table. Okay. It is just that the priority used is slack rather than height of an instruction and so on. So, obviously, the software pipelining algorithms are much more complex than instruction scheduling algorithms, and the problem is NP complete. So, what does it involve? It involves finding initiation interval for successive iterations, and what does the initiation interval? I already mentioned this. It is the number of cycles after which we start the next iteration. So, it is not necessarily as many cycles as the body of the loop. And finding the II, the initiation interval, is a trial and error procedure. We start with the minimum initiation interval, we will see how to compute this later. Schedule the body of the loop using one of the approaches below, and then check if the schedule length is within the bounds, that is II 0 to II minus 1. So, if we have discussed, we are going to discuss strategies later, but the approaches would be either operation scheduling with some priorities computed or use the slack. So, if we have found a schedule for the instructions with between 0 and II minus 1, then stop. Otherwise, increment the value of II, make it II plus 1. For a larger II, there is more, because now the number of time steps available is much more. There is a good chance that we will get a schedule without conflicts. So, of course, we use a modulo reservation table, and schedule lengths are dependent on the initiation interval, dependence distance between instructions, and of course, resource contentions. Let us take a simple example. So, here is the body of a small loop. The instructions are AI plus 1 equal to AI plus 1, then BI equal to AI plus 1 by 2, CI equal to BI plus 3, and DI equal to CI. So, here is the dependence diagram for this particular loop. So, instruction 1 depends on itself, So, AI plus 1 and AI. So, AI is used from the previous iteration and a new one is written. So, the first component is the dependence distance and the second component is the delay or the latency. So, dependence distance is 1. So, we use the result from the previous iteration, and the delay for each instruction is assumed to be 1, just for simplicity. So, this is a loop, and then onwards we have just one no loops again. So, there is no dependence between iterations anymore after this. So, all of them are 0, 1 and 1 is the delay for or the latency of the instruction. Let us start executing the instructions one by one, almost look at the trace of how it goes. So, here is the timeline 1, 2, 3, 4 etcetera. So, we start S1, then S2, then S3 and then S4. So, now we go back and start S1, S2, S3, S4 etcetera, etcetera. So, that is the sequential execution, here would be S1, S2, S3, S4 and so on. So, in this case we are executing just one statement in each cycle or in each time step. But just look at it, the statement S1 depends on itself, that is until the first S1 is completed, we really cannot start the second iteration S1. Okay. That is what this dependence really is. So, if we assume that this is satisfied, so let us start S1, then when we go to the second cycle, we start S2 of course, second time step, but in the same time step we also start S1 for the next iteration, because there is no dependency between this S1 and this S1 really requires results from this S1. So, that is already executed. So, there is no dependence between this S2 and this S1. So, there is no problem as far as dependencies are concerned. Then when we start S3 of this first iteration, we would be executing S2 of the second iteration and S1 of the third iteration is begun. So, in other words, we are trying to execute 3 statements all from 3 different iterations in the same cycle. Then we go to S4, then obviously S3, S2 and S1 are there and there are no more instructions. So, the stable state of this particular sequence would be S4, S3, S2, S1, S4, S3, S2, S1 and so on. Finally, after the number of iterations that is required is over, we execute the rest of the instructions S4, S3, S2, S4, S3 and finally S4 and stop. Here this steady state we are going to execute 4 instructions in each cycle, S4 of current iteration, S3 of next iteration and then S2 of next plus 1 and S1 of next plus 2. So, all the 4 instructions are being executed in the same cycle and we are assuming that there are enough resources, integer units, floating point units, branch units, load store units etcetera available and there is no resource conflict between any of these instructions. So, there are plenty of resources. So, all the instructions can be executed. There is no dependence between these instructions across iterations except for S1. So, we can do this. So, in other words, just the loop now actually is actually one instruction, or rather one complex instruction consisting of these 4 instructions from 4 iterations. So, that is the kernel of our loop. So, and these are the 4 instructions which we are going to execute again and again as many times as necessary. Let us take another example and here we go down one step and look at machine level instructions just for the sake of information. The loop is very simple, ai equal to s star ai and it executes a number of times. Initially let us assume that variable t0 contains 0, variable t1 contains n minus 1 and t2 contains s. So, now we actually do T3 equal to load a comma a of T0. So, this right hand side is being loaded now, then T4 is T2 star T3. So, that is S star ai and a T0 equal to T4, that is this particular item is being stored. Then we need to go to the loop branching part. So, we increment T0 by 4, that is our I, 4 bytes per this is the address rather, T0 is 0. So, we would like to assume 4 bytes per element of the array. So, T0 plus 4, then the counter is T1. So, that is T1 minus 1 and we check whether T1 greater than or equal to 0 and keep iterating. The dependence diagram for this particular loop is here. So, I0 is the load instruction, then it feeds to the multiply, that is I1, and multiply feeds to I 2. Okay. So, in the meanwhile, I 3 is add instruction which is independent of any of these, but that also feeds to I 2. Okay. So, that is the only thing, all right. Then we have this I 3, again there is a self loop. So, the reason is this is I 3 T 0 equal to T 0 plus 4, all right, and then I 2 is a store instruction. Finally, I 4 is a subtract instruction and I 5 is the branch instruction. So, the dots on these indicate that there is a dependence backwards by one iteration. So, for example, I 3 here is T 0 is equal to T 0 plus 4, okay, and this value of T 0 is used in the next iteration. So, that is A T 0 here. Okay. So, that is why this dependence, and similarly I 3 this is the old value of I 3 and this is the new value of I 3. So, there is a loop, and finally, from S 3 this value is used here in the next iteration. So, that is the other iteration, the other dependence that is shown here. Similarly, I 4 has dependence to itself and then it feeds to I 5. Okay. So, this is the loop structure. Now, the number of tokens on an arc indicates the dependence distance. I explained this already. Assume that the possible distance from I 2 to I 0 can be disambiguated. In other words, if you look at this A T 0 and then the store, that is I 2. So, there is obviously a dependence between these two. This load must happen and then the store, but let us assume that it can be handled by hardware in some way. Okay. Software pipeline has to actually respect this particular dependence diagram. So, assume that there are two integer units, each latency is 1 cycle, two floating point units, latency 2 cycles, one load store unit with load requiring 2 cycles and store requiring 1 cycle. Let us also assume that branch can be executed by any int unit, and now a cyclic schedule takes 5 cycles. I will show you this, and it corresponds to an initiation interval of only 1 by 5 iteration per cycle. There are 5 cycles. So, 1 by 5 is the iteration count, initiation iterate. Cyclic schedule, that is the software pipeline schedule, requires 2 cycles. How? So, let us look at this diagram. You can schedule I 0 and then it requires that result to be used by I 1. So, we need to have this as a no op. Okay. There is nothing to do here. Here we can execute I 1, I 3 and I 4, all of them in parallel. There is no dependence between these. Then again this mult requires 2 cycles. So, we hold on, I 2 is scheduled in the 5th cycle along with I 5. Okay. So, that is why we require 5 cycles for the acyclic schedule. This is the regular instruction scheduling. What about the software pipeline? Really, I will show you the details in the next slide. We are going to have this as our kernel or core of the software pipeline. I 4, I 1 and I 0 execute in the same cycle, I 2, I 5 and I 3 execute in the other cycle. So, these two are executed together and I 3 is on another unit. How? Let us look at it. So, iteration 0, iteration 1 and iteration 2 as usual have been unrolled. So, we have load, mult, add, sub, store, BGE in this iteration, in this sequence. Then iteration 1 we start I 0 here and then go on, then again I 0 here and then go on, etcetera, etcetera. Why are we doing this? Why couldn't we have started I 0 here or here and so on? The point is we must have sufficient number of resources to execute the instructions of the second or third iteration in the same cycle. We can't start another load here because load requires 2 cycles to complete and there is only one load store unit. We are assuming that more than one load cannot be issued at the same time by the unit anyway. So, that is the reason why I 0 has to start here. Okay. So, this of course is subject to dependencies and then this is again subject to dependencies within the loop and this also in the same way. So, if you observe at this point we have reached some kind of a steady state and this pattern repeats I4, I1, I0, I2, I5, I3. So, again after this is you know, so this I4, I1 and there will be I0 here if we had peeled iteration 3 as well, I2, I5 and I3 and so on and so forth. So, the same pattern repeats, right. So, because of that this is the stable state of the software pipeline and all the instructions in the loop are in the kernel of the loop, this particular part, see. So, there is I0, I1, I2, I3, I4 at various places and the dependencies are also satisfied because for example, I1 feeds to I2, right. So, here I1 is here and I2 is here. So, this I1 is here and this I2 is here. So, in this the loops are also shorter, okay. Many instructions are executed in the same cycle, but they are all from different iterations. So, there is no problem regarding which result is used by which one. The register allocation would be done appropriately to make sure that results are handled appropriately. What should be remembered here is that many instructions can be executed in the same cycle and these instructions from different iterations. One more example. So, here is a small loop consisting of many instructions of this kind T0 I equal to A I plus B I, T1 I equal to C I star constant etcetera etcetera. Here is the dependence graph for this particular small example. So, 0, 1, 2 the operations are written beside the numbers or at the base level, then 3, 4 are dependent on them and finally, 5 is dependent on 3, 4 and then there is a cycle. Okay. So, this is the cycle that we have. So, the delays are all the distances are all 0 for all these instructions except for this, there is a distance of 2. So, you can see that that distance is created because of this E I minus 2. Okay. So, this E I is computed in instruction 5, E 2 is actually E I minus 2. So, there is a dependence distance of 2 between instruction 2 and instruction 5. Now, let us unroll the loop. So, once you have unrolled it, you will see that these are the 5 instructions 0, 1, 2 can all be executed in a single cycle, 3, 4 in another cycle, 5 in another cycle. So, let us do so. So, we have this group, then this group, then this group for the various iterations of the loop. So, once we reach this point, we know that we have a stable state. How to detect this? That will be through the algorithm later. So, we have 3, 4, 5, 0, 1, 2. So, this pattern repeats. So, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2 and again 3, 4, 5, 0, 1, 2, the pattern would repeat. So, our software pipeline kernel consists of the same 3, 4, then 5, 0, 1, 2. So, we just say PS 0, PS 1 because these are stages just to show that they are not from the same cycle. 3, 4 and 5 are from the same iteration, 0, 1, 2 are from a different iteration. Okay. So, this is time cycle 0, this is time cycle 1. So, this is the loop which would be repeating as many times as necessary. So, this is the concept of software pipelining. We try to execute many instructions from different iterations in the same cycle, in as many cycles as possible. So, now let us start looking at the algorithm for software pipelining. We need to compute what is known as the minimum initiation interval. How many cycles need to pass before the next iteration can be begun. So, that is minimum time before which successive iterations cannot be started. So, MII is the maximum of ResMII and Rec-MII. So, what is ResMII? This is the minimum initiation interval that due to resource constraints, and Rec-MII is the minimum MII due to recurrences or cyclic data dependencies. So, let us elaborate. So, resource minimum initiation interval ResMII is very difficult and very expensive to compute exactly. So, it is almost like solving the problem before we compute it. For function pipeline function unit, it can be approximated as maximum of NR by FR over all the resource units R. So, what is NR? NR is the number of instructions that execute on a functional unit of type R, and FR is the number of functional units. So, you look at all the instructions in the loop body which execute on a particular type of resource, okay, and then divide it by the number of resource types, number of function units of type R. So, that gives you ResMII for that particular resource. So, you do this for all the resources and then take the maximum. So, let us look at an example. So, the previous example, here is the graph, and we know that there are 2 integer units, 2 FP units and 1 load store unit. So, that is if you count the number of instructions of each type. So, int, FP and load store. So, we have add, sub, then this BGE, which is again a branch instruction, which are executed in the int ALU. There is only one mult instruction, which is the floating point variety. So, 1, and then there are 2 instructions, load and store. So, that is 2. The number of int units is 2, FP units is 2 and load store units is 1. So, the maximum of all this is 1.5, 0.5 and 2. So, that is 2. So, resource MII is 2, that means you cannot have a software pipeline kernel of length less than 2. So, what we got here was really a software pipeline kernel of length 2, that is the optimal part. Okay. So, then for non-pipeline function units or function units with complex structural hazards, ResMII is defined as max over all the resource function units, right, all the resources of sigma n a comma r over all a. So, a is the instruction, okay, and then n a comma r represents the maximum number of time steps for which instruction a uses any of the stages of a functional unit of type R. So, if I am using any particular resource, okay, it does not matter which stage of that resource, I account it for the function for the instruction A. So, I sum up all the requirements of the instruction A, that is sigma over all, and then sigma over all A, right. Then divide it by the number of function units of type R, so, and take the max for all such resources, you get the ResMII. So, let me show you an example. So, let us say these are the reservation tables for int unit, LD store unit and function unit. These are purely fictitious, okay, not that this is possible in practice. So, now for instruction I0, which is a load. So, load would require 2 units of R0, 2 cycles of R0, 2 cycles of R1 and none of R2. So, R0 is 2, R1 is 2, and then I1 requires it is a floating point instruction. So, it requires all in this FP unit. Okay. So, we would require, this is a slight mistake, this should have been 1 1 1 here. So, R2 is required 3 times, the rest are all 0, and then I2 would require R0 2 times and R1 2 times. I3 would require R0 2 times, R1 2 times and so on and so forth. So, now if you sum up all the R0 requirements, you get 8, you will sum up all the R1 requirements, you get 8, and R2 requirements, you get 6. So, divided by so this, this is the number of resources. R0 is available in 8 units, R1 is available in 8 units and R2 is available in 6 units. Why? We have 2 integer units. So, R0 is required in 3 phases. So, we rather we would say we have 4 into 2, 8 of these 0 0, this is 1 2 and R0 is required here also 1 and 2. So, as I said, this should be zeros, only these should be 1s. Now, R1 is required, we would have 8 resources again, because 2 of this and 2 of this, 4 into 2. So, again 8 resources, and R2 would be required available in 6 resources. So, if this is 1 1 1 each, we would have 3 of them, and then into 2 would be 6. So, then you divide, this is just an assumption, that so many units of R0, so many units of R1, so many units of R2, etc. are available. Now, you divide 10 by 8, 10 by 8 and 3 by 6. So, you get a max of 2. So, with a complex pipeline, this is what you really do. You count the usages of the various units divided by the number of units of that kind. So, you get ResMII. Then what is recurrence MII? So, the recurrence MII initiation interval is actually the minimum initiation interval due to cycles. So, this is dependent on the cycle length. So, both the delay length and distance length in the dependence graph. So, it is defined as max over all the cycles. So, what we really do is you enumerate all the cycles, take one cycle at a time, compute delay in the cycle, divide it by the distance in the cycle. So, take the max over all cycles, that will be your ResMII. So, let us see how to compute it. So, for this example again we have two cycles here, one is here and the other is here, right. So, this is a delay of 1 and distance of 1, this is also a delay of 1 and distance of 1. So, we have 1 by 1 and 1 by 1. So, the max is 1. So, for ResMII this would be 1. So, initiation interval ResMII was actually 2 for this example, ResMII is 1. So, the minimum initiation interval would be max of this, that is rather the minimum of this, that would be just 1 or 2. So, we actually have for example, in this case, right, we really say MII is the max of ResMII and ResMII, not the min, even though it is the minimum initiation interval. The reason is the restriction on the resources or the restriction on the cycles will stop you from initiating the next iteration. So, you really cannot take minimum here, it has to be the maximum. Now, let us take another example. So, we let us compute the ResMII and ResMII for our cluster example. So, here is the code and this is the dependence graph. So, if you look at it, now you have ResMII, you really have only two types of instructions, this and so adder. Okay. So, 2 multipliers, 2 adders and 1 cluster. So, you have just 1 and 2 multiply instructions and 4 add instructions. So, 4 adders and 2 multipliers. So, add instructions and we have 2 of each. So, 4 by 2 and 2 by 2. So, that would be 2 comma 1, the maximum is 2. So, ResMII is 2. So, we really have minimum possibility of 2 because of ResMII for the kernel length. What about ResMII? It is actually, you have to take the cycle, there is only one cycle. So, no question of taking a max there. So, add the delays and distances. Okay. So, if you add the the delays 1 plus 1 plus 1, so that is 3. You add the distances 0 plus 0 plus 2, that is 2. So, 3 by 2 is 1.5 and its ceiling is 2. Okay. So, ResMII also says 2, ResMII also says 2 and we have demonstrated that it is possible to get a software pipeline of length 2. So, in this case we have achieved it, but in general you may not be able to get a software pipeline of length MII, you may actually get something more than that, okay, because of difficulties in scheduling. So, what is the algorithm? The algorithm is you compute the minimum initiation interval and set the II value, initiation interval value as MII. So, we are going to try and get a software pipeline of length MII the first time. How to do that? You compute we are assuming that some distance height etcetera is used, not the slack. So, let us compute priority for each node. Okay. So, what are the priorities? Height of a node is one of the priority functions and we are going to say how to compute it a little later, and height is computed using both the delay and distance components of the dependence graph, okay, or on the arcs we have this dependence, the delay and the distance. So, we are going to use it to compute the height. So, let us assume that priority, that is height, is computed for all the nodes. Choose an operation of highest priority for scheduling. So, pick up, this is operation scheduling. So, there is no ready queue. Okay. So, we are just going to pick up the highest priority the node and start operation and start scheduling. So, how to do that? You compute earliest start time for the operation. Again, we are going to show details of this a little later. So, now you start and try to schedule the operation between the in the interval E start and E start plus II minus 1. Why? Why should we try scheduling the instruction in this range? The reason is the software pipeline is supposed to be of length II cycles, and every II cycles we are going to begin a new iteration, right. Now, we are looking at the instructions of the loop in one iteration, that is the body. We must be able to fit all the instructions of the loop within a window of II cycles. That is why E start is the earliest start time for an instruction. So, we look at E start plus II minus 1. Okay. So, all these are modulo II. Okay. So, if we go beyond II slots, we actually wrap around and come from the top. So, we try all the instructions E start plus 1, E start plus 2, etcetera, modulo of course II, and see if we can fit these instructions into these slots. But then checking whether the instruction fits into a slot implies checking for resource contentions. So, if there are not enough resources, then we can schedule it, otherwise no. How do you check resource contentions? That is where the modulo reservation table that I mentioned earlier comes into picture. MRT records resource usages in every cycle. So, you just check whether the resource that you need for this particular instruction is available, if so schedule it. So, now if the that is 5, this is 6. Okay. So, if a slot is available, then schedule the instruction, no problem as such, and this may involve actually unscheduling those immediate successors of the instruction with whom there is a dependence conflict. Why? So, now this is operation scheduling. So, we just picked up the instruction, computed its E start and put it there. It may so happen that some other instruction which is following it in the dependence graph may be scheduled in an inappropriate slot. That may happen because of the step number 7, which we are going to see later. Okay. So, we have just put there is some other instruction which is now colliding with it because of the precedence problem. Okay. So, it has happened. Now, we actually must remove the successor which is colliding with our instruction which has just now been placed, and perhaps the removed instruction will find a different slot in the next scheduling cycle. It is not possible to have any resource conflicts because we have already checked whether resources are available. Okay. So, now whatever precedence conflicts happened because of the successors were all removed. So, they will be rescheduled again. So, suppose we are not able to find a slot, that means the slot has already been occupied by somebody, there is a resource contention in every slot in between E start and E start plus II minus 1. Now, just choose E start if the instruction has not been scheduled so far. This is the first time that we are scheduling the instruction. So, in that case you choose the E start slot and forcefully fit that instruction into the E start slot. If we forcefully fit an instruction there, then actually there may be some instructions which are already fitting there. So, we have to remove them, and that means unscheduling those instructions and remove them, and finally, schedule them in some other slot later on in the second cycle, third cycle, fourth cycle, and so on and so forth. So, suppose choose priv minus shed time plus 1 if the instruction was previously scheduled at priv shed time. So, this is the first time we are using, then E start. If it is not the first time, then it would have been scheduled previously in a slot, let us say priv shed time. So, we use priv shed time plus 1 if the instruction was previously scheduled at priv shed time. So, we could not actually schedule it we had scheduled it previously, but then it was kicked out and so on and so forth. So, that is why we are rescheduling it now, that is what we mean. So, in the previous time we had scheduled it at the priv shed time. So, now add 1 to it and try the next slot. This will invariably involve unscheduling all the instructions which have resource conflicts with the instruction being scheduled. So, there may be instructions in the current slot or the next slot and so on and so forth, which now collide because of resource contentions. So, all these are now unscheduled, and we are going to try scheduling all over again for these removed instructions. So, this looks like a very violent case with too many instructions removed and so on. No, not necessarily. So, the fear may be that there may be failures and we may be going in a cycle, each instruction removing something else. So, like just like the thrashing problem of operating systems. No, we are going to keep a counter. If there have been too many failures of the type 6 or 7, then increment the initiation interval and repeat the steps. So, once they pass the counter value for this thrashing, we cross the counter value for this thrashing, we say this initiation interval is not good enough for us, maybe we need a larger initiation interval with extra space. So, extra cycles. So, we increment the II and repeat the scheduling all over again. So, all the partial schedules are thrown away and scheduling is started fresh. How do we compute E start and height? So, we know that we are going to use operation scheduling. So, operation scheduling implies that there is no ready list, because unscheduling of previously instructions is possible here in any operation schedule. So, ready list has no value. We use an MRT with II columns and R rows. So, to record the commitments of scheduled instructions, I have already explained this before. Conflict at time t implies conflict at t plus k star II and t minus k star II. So, this has to be checked. Okay. So, rather this is certain. So, k equal to 0, that means t, that is a conflict. K equal to 1 implies t plus II and t minus II. So, all these are modulo II. So, that is why if we are going to begin another iteration II cycles later, conflict at t implies conflict in the next iteration also, which is started II cycles later, and there would have been one iteration running II cycles earlier also. So, conflict at t implies conflict in the previous iteration and the successive iteration, which were started minus II cycles before and II cycles later. So, that is what this really says. So, what is E start? So, earliest start time is 0 if q is unscheduled. What is q? Q is a predecessor of p, and so we are going to consider only scheduled predecessors in the computation of E start. Unscheduled predecessors are not used. Otherwise, if it is already scheduled, then max of 0 comma shed time of the predecessor q plus delay of the arc from q to p minus II star distance q comma p. So, this is the moderating factor. So, this modulation which is introduced by the moderating factor make sure that we take all the factors available to us for the computation of E start. Okay. So, height is similarly computed as 0 if p is the stop pseudo op, the last one, because we compute from the bottom upwards. Okay. And it is the max of height q plus delay p comma q minus I star distance p comma q. So, very similarly again this distance p comma q, this is the factor which modifies the height, otherwise it would have been the height computed as in the case of instruction scheduling. Okay. So, now there is a modulating factor here, that is the distance star I. So, E star p and height p are computed in this fashion and they are used for the scheduling as I described before. Now, so far we did not worry about any register requirements and what happens if there are not enough registers and things of that kind. So, let us start looking at that particular problem. So, instances of a single variable defined in a loop are actually active simultaneously in different concurrently active iterations. So, let us look at the figure. So, in the figure value produced by I 1 in time step 2 is used by I 2 only in time step 5. So, here is the figure. So, I 1 produces a value in time step 2 and I 2 actually uses it only in time step 5. Okay. So, that is what is here. So, now what happened, because of the software pipeline here, okay, another I 1 has already begun, right. So, this I 1 had actually produced a result, this I 2 had not yet consumed the result, but the next I 1 has already started. So, it should not happen that whatever I 2 is supposed to store is already overwritten by I 1 even before I 2 uses it, that is what is the problem here. So, another instance of I 1 from iteration 1 in time step 4 could overwrite the destination register. So, assigning the same register for each such variable would be incorrect. So, in other words, this variable which is computed by I 1 and written into by I 2 in the iteration 0 must get a register which is different from the register which is assigned to I 1 and stored by I 2 later on. Okay. So, this register and this register, they are in two different iterations, but they are probably going to execute together. Okay. So, this register and this register must be separate, that is the basic idea. So, automatic register renaming through rotating register sets is one hardware solution. So, automatically for each iteration the register numbers are changed and a set of registers is available again for the loop to be for the instructions to use. So, there may be let us say a register R 0 available to I 1 in iteration 0. So, this becomes R 0 prime in the second iteration, R 0 double prime in the third iteration and so on and so forth. So, that is what we mean by a rotating register set. There are a set of registers, a vector of registers, one for each iteration. Okay. For the R 0 itself will have different instances, one for each iteration. So, that is one hardware solution. Unrolling the loop as many times as I and that is the maximum, okay, and then applying the usual register location is another problem, another solution. This is called as modulo variable expansion. So, this process essentially renames the destination registers appropriately, but increases the II as well. So, what happens here is I 1, here is I 2 in iteration 0, here is another I 1 and I 2 in the next iteration. So, suppose we unroll the loop. So, we have II of 2 here. So, these instructions will all be here. Okay. So, we have unrolled the loop, then we assign two different registers for this I 1 and this I 1. Okay. So, automatically this I 2 and this I 2 use two different registers by the usual register location, and then we find a software pipeline. There should be no difficulty in this case, because there can only be two instances of I 1 active in any two instances of the result of I 1 available active at any in any kernel. So, since we have taken care of renaming the registers, so there should be no difficulty. But then we have unrolled the loop. So, that means the number of instructions in the body has increased. So, we may have to increase the initiation interval and the efficiency may become lesser. So, what about register spilling? So, register requirement is higher than the available number of registers, then we spill a few variables obviously. Register spills need additional loads and stores. So, if the memory is already saturated, then we may have to actually increase the II value and retry, or we could reschedule the loop with a larger II, but without inserting the spills. Okay. So, but increased II in general reduces register requirement. So, this may be all right. Generally, it is better to spill and then increase the II if necessary, rather than straight away increase the II and schedule the code. Now, what happens if there are if then else branches inside the body of a loop? We can perform what is known as hierarchical reduction. So, two branches of a conditional are first scheduled independently. So, then and else parts are scheduled independently. Now, the entire conditional is then treated as a single node. How? Resource requirements of this entire conditional is the union of the resource requirements of the two branches. Why? The reason is each one of either one of the branches is going to be executed, not both. So, we just take the union of these. Then the length of the schedule latency is equal to the maximum of the lengths of the schedules of the branches. So, again the same reason, only one of them will be active at any point in time. So, now we have reduced the entire conditional to a single pseudo op with resource requirements and the delay. Now, we schedule the loop. Okay. So, after the entire loop is scheduled, conditionals are reinserted. So, the loop is back to its original shape and then it is used. The second possibility is do if conversion. So, if you convert if statements with predicates, then the body of the loop blows up. If there are 4 statements in the then part and 5 statements in the else part, now the if converted body will contain 9 statements. So, scheduling the predicated body involves more resource usage here. So, it is actually the sum of usages of the two branches, it is not actually the union as in the case of hierarchical reduction. So, you really require more resources, there will be more resource contentions as well. So, in general after if conversion you may actually end up with a higher II than in the case of hierarchical reduction, and further you will also need predicated instructions and the hardware support for all this. So, this gives you an overview of software pipelining, the algorithm and the issues of register location, etcetera, etcetera, etcetera. So, this is the end of the lecture. Thank you.